are going to start with deletion. In the last class we saw how to do insertion, search, computing successor, computing predecessor, computing minimum, maximum in a binary search tree. Today the only one operation that is left is the one of deletion. So, we are going to see how to do deletion in a binary search tree, and then we are going to address the question that I had raised in the last class, which was that if I were to insert the elements in a random order. So, I have to insert some n elements into a binary search tree. Suppose I were to randomly permute my elements and insert them, right. So, then what is the what can we say about the time that the insertion would take? Yeah, we will see all of that today. So, deletion operation, so essentially is the following: you are given a node x in the tree and you have to delete the node, right, and we will distinguish three cases. X has no children, which will be the easiest case for deletion. X is a leaf in that case, right. If x has only one child, even then the case is very easy, and we will see all of that. And when x has two children, it is slightly more tricky, but still fairly straightforward. So, when x has no children, then deletion is trivial. Why is that? So, this is the node x, yeah, it does not have any children. So, it is a leaf and I need to delete this node. So, what should I do? I should just cut this link, which means that the parent of x, we will have to change either the left child or the right child of this parent. So, in this case b was the right child of the parent. So, we will have to set the right child of a to null now. Is this clear to everyone? Yeah. So, if b were the left child, then we would have set the left child of a to null, and after the deletion this is the tree that would be left for you. So, if the node that you are trying to delete is a leaf node, then the problem is trivial. Yeah. What happens if the node that you are trying to delete has only one child? So, you are trying to delete a, it has only one child, which is b, right. A does not have a left child. Okay. Now, what can we do? So, again the operation, it is like this, you can think of this part as just a linked list now. Yeah, this is just like a linked list, and you are trying to delete a node from the linked list. So, what do? You take the previous node, which will be d, and you will make its left child now point to b. Right? So, effectively you are removing these two links and you are establishing this link directly from d to b. Are you convinced that this would maintain the search property? Why should b be on the left of d and not on the right of d? Because b is less than d, right, because b is in the left subtree of d. Yeah. So, we would make this the left child, and everything that is below b, all descendants of b, are also less than d because they are all in the left subtree of d, right. So, we will just continue with them as they are, there is no change there. The only change that happens is that these two links go away and you set up this one link. Is this clear to everyone? Questions? Right. So, nothing to be done even in this case, or very little to be done. Yeah. So, this will be the new setting, or this is what will happen after the deletion. You have d, you have b, and you have f, a goes away. Right. The third case is when the node to be deleted has two children, right. So, maybe x is the node to be deleted, which is x is a reference to the node which is to be deleted. So, the node to be deleted is the one containing d now. It has two children, right. So, what do we do now? Okay. So, since it has two children, we can, let us say, let us do the following. It has a left subtree, it has a right subtree. We will find the predecessor of d. How do you find the predecessor of d? We have seen how to do successor, but we also said you can equally find the predecessor. How do you find the predecessor? Well, the predecessor of d would be the largest element in the left subtree. So, we just have to come left and keep going right. So, since b does not have a right child, so b is essentially the predecessor of d in this example, right. Now, how many children does b have? 0. Wrong. How many children does b have?
1.
At
Be at
most
most
1.
one.
It can have 1. b can have a left child. Nothing preventing us from b having a left child, right? So I could have a situation in which let's say what T, we could have something like this. Yeah, but B does not have a right child. There is nothing here. If B had a right child, then it would not have been the successor, the predecessor of D, because we would have gone down further. Yeah. So B has only one child or no child. This need not be there. Yeah. So that's what is being said here. B or Y is the same thing. Y is the reference and B is the content. So sometimes I'm calling it B, sometimes I'm calling it Y, but this has at most one child. Okay. Now what do we do? Anyone? What do you think you'll do? So let's get rid of this. We are going to delete B
and then replace D with B.
T with B and D with B.
And essentially we are going to move B here. So this is not, we are not establishing such a link. We are not establishing this link, but we are going to replace this with B, right, and delete this node. Just get rid of this node. Okay. Why can I move this here? Well, why would the search property not get violated by moving content of B here? Because since this is the successor, B was the successor of D, everything in this left subtree was less than D, and B is the largest element in this left subtree. So everything in this left subtree is also less than B. Yes? So everything in this left subtree is less than B. So if I move B here, there is no problem as far as the search property is concerned. Everything in the right subtree is more than D. Yes? And so it's also more than B. So by moving here, the search property again is not violated. So I can move B here, and now why can I delete B easily? Because B has either no child or one child, and we've seen already how to do that, right? How to delete a node which has no child or only one child. Any questions on this? I see some frowns. What don't you understand? Yes?
Sir, if B has one child,
Yeah.
then we have to replace the left subtree of B, the first element of the root of the left subtree of B,
Right.
to B.
You're saying if B has one child,
Yes, sir. Yes, sir. It has
suppose
left
B
subtree.
had one child. B, if it has one child, it will have only a left child. It cannot have a right child.
Sir, it can have a left subtree.
It can have a left subtree. Let's say it has something here, right? Now what?
Then, sir, when we have to shift B, then we have to make the root of the left subtree.
No. So okay. So good question. So you are worried. Suppose B had a left subtree here, right? And suppose I decide to move B here. Okay. Now there is nothing left here. So we said we'll delete this node. When we delete this node, what happens? We'll
This
make
goes
this
to
right
end.
child point to here, and that's it. Okay. So this gets deleted. This link and this link go away, and we create this one link, and it points directly to here, and this moves up there. Doubt? Okay, great. Yeah, so that's the operation. So now we have covered all the three cases. Everyone recalls? So the first case was when there was no children, second case was one child, third case was two children. And we said in the third case we will have to replace, we will have to move the content of this node to there and then delete this node. Okay. So we worked with the successor, but we could also have worked, we worked with the predecessor, but we could also have worked with the successor. Since this has two children, we can also find the successor of this node by going once right and then keep going left. The same kind of a thing could be done even there. right? We could have replaced this node with its successor instead of its predecessor. Yeah, but in this example I had shown the predecessor, which is why I worked with predecessor. Everyone understands this? So what do you think is the running time of the delete operation? Suppose you don't even have to search. I tell you that this is the node, I give you the reference to the node that you want to delete, right? How much time does it take to delete? In the first case, when the node is a leaf, how much time would it take? Order 1, because I just need to go to the parent. There is a pointer in the node, a reference to the parent node. I just go to the parent and I just update the link, the right or the left child of the parent, whichever it is.
The reference, you are actually giving the reference of the parent. Anything, child.
Now I am giving the reference of the particular node which has to be deleted.
So if you give the reference of the node, we don't have a back pointer.
We have, in every node we also have a parent, a left child, a right child and a parent. Yeah. So we can always go back to the parent and update the content, right, to show the deletion. If we have, if in the second case when we are, if we are deleting this node, then once again we go to the parent and modify its left child. Again a constant time operation. So in which case do we take more time? In this case, because here we have to find a predecessor or a successor. Predecessor can take time as large as the height of the tree, because we will have to go once left and then keep going right. Yeah. So we can take, in the worst case, time proportional to the height of the tree. Okay. So that will take, so this is the case in which we take the most time. And how much time do we take in the worst case? Order the height of the tree. So this is pseudocode for the deletion, just so that you understand roughly what is happening. We don't have to look at it in great detail. If the left or the right is null, then what do we know? That either it's a leaf node or it is a node with only one child. Yes. Then in that case, so Z was the node which I am trying to delete. So Y is, let's say Y is Z, and we look at the tree successor of, Z. Okay, I am not completely sure that I have this right. So let us just skip this, right? You understand what the delete operation is. So I might have made some mistake somewhere here.
So B was the predecessor in the previous part?
Pardon?
B was the predecessor in the previous
Predecessor or successor is the same thing, right? We can also work with the successor, that's what I said.
Your successor, we'll have to search in the right.
For the successor, you'll have to search in the right. Okay, so I don't think that's very critical, but let's skip this thing for now. Okay, so you understand delete. The pseudocode you can all write yourself. Okay, now suppose I give you a binary search tree. This is a binary search tree, and I do an in-order traversal of this binary search tree. Right? Now what does in-order do? Someone tell me. First the left, then this node, then the right. So first we will be printing out all these keys. Yes? So suppose all I do when I visit a node is print out the key. Yeah, suppose that's what my traversal procedure is. So first I will be printing out these keys in some order. I do not know which order, but I will first print out these keys. Then I will print this out, and then I will print out these keys. Right? So which means that I will print out the root key 5 after I have printed out the left and before I print out the right. But all of these keys are less than or equal to this, and all of these keys are greater than or equal to this. So which means that 5 really comes at the right place in a ordering of these keys. Okay? Because everything that is less than 5 comes before 5 and everything that's more than 5 comes after 5. So 5 comes at really the right place. And the same argument can be said for every key, not just the root key. When will I print 3 out? After I've printed everything to the left, yeah, then I'll print 3. So everything that is smaller than 3 will come before 3. yeah, and then I will print out things on the right. So, the in order traversal, so if you were to just look at this and see how you would, in what order you would print out, you would first come here, then go left, then come here, you will print this one out, then you will print 3, then you will print 5, then you will print this 5, then you will come right, first go left, so on and on, 7, 10, 11. So, this is the order in which you will print the keys. Yeah. So, an in order traversal of a binary search tree, so what is the property that it has? It prints out the keys in increasing order. Yes. So, this can be a good method of sorting a bunch of keys. Yeah. So, I'll call this the binary search tree based sorting procedure. So, what is the method now? Well, you have a bunch of keys which you want to sort. So, what should you do? You first insert all the keys into a binary search tree. So, that is what you are doing. You are taking all the keys and inserting them into a binary search tree, and then just do an in order traversal of this tree. So, you will get all the keys in increasing order. So, you sorted your set of keys. Yes? Is this clear to everyone? So, how much time does this procedure take? We have to insert all the keys, and then we have to do an in order tree walk. So, let us first look at how much time does the in order tree walk take. How much time does it take to traverse the nodes of a tree in order? Order n. Why order n? We have to print all the nodes, but yes, but I may take much more time, right? I need at least order n time, but at least n time, but why don't I, maybe I need more time.
So it will be n square.
Pardon?
So it will be like n square.
It will be like n square.
For each, you have to search first.
You have to go to the leftmost side each time when you are covered the left submost tree. Then while going to the right sub tree, you have to go to the left.
So we have to
leftmost
do
side.
each
Which will
node
take
a
more time.
finite number of times, not more than 3 times.
That was for an earlier walk that we had said that each node will be visited thrice, right? Not for an in order traversal.
Twice.
Okay, so we'll look at this question later. Okay, how much time does it take to do an in order tree walk? Actually, it just takes linear time. It takes order n time. Okay, but we'll not do it in today's class. We'll see how to argue that it just takes order n time. So those who said order n is right. Okay, how much does this part take when I'm inserting all the elements into a tree?
N log n.
N log n? Why n log n? Okay, so this is my BST sorting procedure. I want to sort these keys. I insert them into a binary search tree, one after the other. So first 5, then 10, then 7. Then when I insert 1, it will go as the left child. Then I insert 3, it will go as the right child of 1. When I insert the other one, it will go as a left child of this one, of this 3. It depends upon how you are doing. It could also have come as the left child of this one. It's the same thing. And 8 would come as the right child of 7. And this is the tree you would get. And now if you were to do an in order tree walk on this tree, you would get exactly the sorted sequence. So that brings back to the question that I asked you earlier. Brings me back. So how much time does it take to insert all the n elements?
It depends upon the sequence.
It depends upon the sequence. Exactly. So if I were to sort, let's say I'm given a set of numbers 1 through n, and I just want to sort them. Yeah. So what the total time taken to insert these numbers is equal to the sum of the levels at which the nodes will come up, right? Because when I insert a particular number, I come down the tree and I insert it at a particular place, right? So the number of levels I traverse or the number of comparisons I do before I am able to insert it is exactly equal to its level. Yes or no? Either level or level plus 1 or level minus 1, but you can think of it as the level for now. Right? So if the numbers were in sorted, if I had inserted the numbers in sorted order, right? First I inserted 1, then I inserted 2, then I inserted 3 and so on, then what is the kind of a tree I would get?
Straight, only right.
I would have 1 followed by 2 followed by, yeah, so you remember that kind of a picture. I would get a tree which looks something like the following: 1, 2, 3, 4, n. Yeah, and what is the sum of the levels? 0 plus 1 plus 2 plus 3 up to n minus 1, right? And this series sums to n squared. Okay, so that's not good. The time taken for insertion could be as bad as n squared. Is this clear to everyone? Now suppose, so this brings back to the question that we had asked in the last class. Now what I do is I don't insert the elements in the, I take a random permutation of the elements. I take a permutation of these elements, right? There are n factorial different permutations. I take one of them at random and I insert the elements in this particular order. Okay. Now I want to compute what is the time it takes to insert. Right. So the time required for insertion now is a random variable. Yes. We saw an example where the time required for insertion could be as bad as n squared. Right. That's what I showed you on the previous slide. Right. In the best case, it could be actually quite small, and we'll see what the best case is. Right. So it's really a random variable. It depends upon what sequence, what is the permutation in which we are inserting the elements. Right. In fact, we had discussed the best case in the previous class, right? We said the first element inserted should be n by 2, right? And then it should be n by 4, and then 3n by 4, and so on and on. Although we have not computed what the value of the total time for insertion there would be. Right? So it's really a random variable, the total time for inserting these n elements. Okay? And for random variables, we compute what is the expectation of the random variable. Right? So recall, what is the expectation of a random variable? So if a random variable takes many different values, then the expectation of a random variable is obtained by taking the average. By taking the average, if each of those, if the probability of each value is the same, right? Otherwise, what do? You essentially do many trials, which means that you compute the value of the random variable, then you compute, you do the experiment once again, and so on. Look at the value of the random variable that you get, and then take the average over all the trials. Right? That's how you compute the expectation of the random variable. In our case, it's easier because each of the permutation is equally likely. Right? We are saying we'll just pick one of the permutations uniformly at random. So each of the permutations is equally likely. So we are going to see what is the time it takes to insert the elements given by a certain permutation, insert the elements in the order given by a certain permutation, then the time it takes. So how do we compute the average? We will take a permutation, insert the elements in that order, compute the time it takes to do that insertion. Then take another permutation, compute the time it takes to insert the elements in that order. Take a third permutation, compute the time it takes to insert elements in that order, and so on and on. Right? And there are n factorial different permutations, so I'll compute the time it takes to insert elements in the order specified by these n factorial different permutations. So you'll get this total time, this huge quantity, and we'll then divide it by n factorial to compute the average, and that will be the expected time it takes. Right? So to summarize, for each of the n factorial permutations, we'll compute the time taken to insert the keys in the order specified by that permutation. Yes, and then we'll compute the average. The average is computed over the n factorial permutations. We'll denote this quantity by T of n. Right? Whatever is this value, that will be T of n. Everyone with me? Right? Can someone tell me what? Let's see. What is T of 2? let us see how we will compute T of 2 or T of 3 is, see how to compute T3 then. So, T3 is the tree obtained or is the expected height of a tree on 3 nodes. Yeah. So, what are the various possible tree on 3 nodes that we get? So, what are the various permutations of elements 1, 2, 3, right. So, we will have 6 different permutations 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. When we have this particular permutation, what is the tree we would get if we were to insert the elements in this order? We would get a tree whose root is 1, 2 would come to the right and 3 would come after that. When elements are inserted in this particular order, we would get a tree 1, 3 to the right, 2 to the left of 3. Elements inserted in this order, we will get a tree which is 2, 1 to the left, 3 to the right. When elements are inserted in this order, we get a tree which is 2, 3 to the right, 1 to the left. When elements are inserted in this order, we get a tree which is 3, 1 to the left, 2 to the right of 1, but to the left of 3. And in this order, we get 3, 2 to the left, 1 to the left. Right. What is the total time taken for insertion here? We recall we said that it is just the sum of the levels of the nodes. So, the levels of the nodes are 0, 1, 2, and so the sum is 3. In this, the levels of the nodes are again 0, 1, 2, so the sum is 3. Here it is 0 and 1, this is also at 11, 1, so the sum is 2, 0, 1, 1, sum 2, 0, 1, 2, sum 3, 0, 1, 2, sum 3, total of 16. And so, the average over all is 16 over 6, which is 2.66, which is T of 3 then. So, we computed T of 3 as 2.66. Right. So, that is what was being said here. For each of the n factorial permutations, we are going to compute the time taken to insert the keys, which is what we did for T3, and then compute the average, right. So, that gives us the value of T3. Right. But we cannot do the computation in this manner, we have to do it cleverly because we have to compute what T of n is. Right. So, I am now going to fix a particular element, let us say I, and I am going to look at all permutations in which the element I is the very first element in the permutation. Yes. So, there are n minus 1 factorial such permutations in which I is the first element. In these n minus 1 factorial permutations, the tree that we obtain will have I as the root because it is the very first element, and then the keys 1 through I minus 1 will be in the left subtree of the root, and the keys I plus 1 through n would be in the right subtree of the root. Right. Now, let us look at one of these permutations. Let us look at one of these n minus 1 factorial permutations and restrict our attention to the I minus 1 keys, to the first I minus 1 keys, to the keys 1 through I minus 1. Right. They will be coming at many different places, they will be coming at some places in this permutation. Right. Now, let me look at another permutation, another one of these n minus 1 factorial permutations. These keys 1 through I minus 1 would be coming at some other place. So, if I look at all of these n minus 1 factorial permutations, they will induce permutations of these 1 through I minus 1 elements also, keys 1 through I minus 1, and every permutation would be there, every permutation of 1 through I minus 1 would be there. Right. In particular, each permutation of 1 through I minus 1 would occur how many times? Right. There are n minus 1 factorial permutations in all, yes, and there are I minus 1 factorial permutations of the elements 1 through I minus 1, and there is no reason why one of these permutations will occur more often than the other permutation. So, each of them is occurring equally likely. So, how many times is each one of them occurring? N minus 1 factorial over I minus 1 factorial times. Yeah, you can also think of it in a slightly different manner, right. You have these I minus 1 elements somewhere, and the other n minus I elements are getting inserted at different places here. So, how many different permutations are there of those n minus I elements that are getting inserted, right. So, you can compute that and it will be exactly this quantity, right. But this is a simpler argument. There are n minus 1 factorial permutations in all, and there are I minus 1 factorial permutations of these elements 1 through I minus 1, and there is no reason why one of those permutations should be more likely than the other one, right. They will all occur the same number of times, it is symmetric after all, right. So, each permutation therefore of these elements is occurring exactly so many times, right. Okay. So, suppose I had keys only 1 through I minus 1, right. I had only I minus 1 keys 1 through I minus 1. Then the average time taken to insert these keys is T of I minus 1. This is what we define T of n as. This average is the average taken over all the permutations of 1 through I minus 1, right. So, the time taken to insert all these I minus 1 factorial permutations is therefore just I minus 1 factorial into T of I minus 1. Yeah. The average time is T of I minus 1, and the average is taken by doing what? By computing the total time to insert all the I minus 1 factorial permutations divided by I minus 1 factorial I minus 1 factorial. So, the total time to insert all the I minus 1 factorial permutations is I minus 1 factorial times T I minus 1. Like for instance, in the example that we did earlier for T3, the total time taken to insert all the permutations was 16 we had computed, right, which was just the average times 6. Okay, good. So, when we are inserting the keys 1 through I minus 1 into the left subtree, so we go back to the previous setting. Recall we are considering only permutations in which the first element is I, right. So, the keys 1 through I minus 1 when we are inserting, they will all be compared first against I, and then we will go and put them in the left subtree, right. So, each key has to be compared with the root which is I. So, now what is it like? It is as if I am creating a tree of I minus 1 elements. Yes, I am creating a left subtree of I minus 1 elements, but I can't just count that as the average cost, because I am also counting one more, because now for each of those elements in the left subtree, their level is actually one more than if it were just the left subtree. So, let me clarify what I am saying. So, this is I, and the keys 1 through I minus 1 are coming here, 1 through I minus 1 are coming here, right. I know something about just this tree. If this were my tree, then I know that the average time to create this tree is T of I minus 1. But now I am creating a tree of over n nodes. The keys 1 through I minus 1 are coming here, and the other keys are coming here. How much time am I spending in creating this part? Well, whatever was the average for this plus one more for each one of these guys, right, because first I compare here and then I come down here, right, because the level of each of these guys is actually one more in this tree than it is in this tree, right. अगर यहाँ पे कोई node है जिसका level 2 है in this tree, then it has level 3 in this original tree. Okay. So, what is the total time to insert all the I minus 1 factorial permutations then? Well, recall T I minus 1 is the average time, T I minus 1 is the average time to insert I minus 1 keys, right. In the tree that I am creating, I am taking 1 unit extra for every node that I am inserting, because first I am comparing it against the node. So, this is the time I am taking to insert the I minus 1 keys, right. This is the average time I am taking to insert the I minus 1 keys in my tree, right, and then this is the average time. So, what is the total time? Well, I have my I minus 1 factorial different permutations. So, the total time is this product. right. Now, each of the permutations, recall, appeared so many times, n minus 1 factorial divided by I minus 1 factorial times. Yeah. So, what is the total time I spend in inserting keys 1 through I minus 1? The total time to insert all the I minus 1 factorial permutations is this much, but each of the permutations is now appearing so many times. So, it is just this times this, right, which is n minus 1 factorial times this part. So, this is the total time I take to insert the keys 1 through I minus 1 into my tree, where this sum is taken over all the n minus 1 factorial permutations, and this is actually not the total time, this is the total time for permutations in which the first element is I. So, to recap, time to insert keys 1 through I minus 1 is n minus 1 factorial times t I minus 1 plus I minus 1. Similarly, time to insert the keys I plus 1 through n will be similar to this, right. Left or right mein there is no significant difference, it is just that yahan pe there are I minus 1 keys that I am inserting, now I am inserting n minus I keys. So, wherever there was I minus 1 here, I will replace it by n minus I, because that is the number of keys I am inserting now. So, that would give me this expression. This is to insert the keys in the right subtree. So, the total time to insert all the n keys then is just the sum of these two quantities, and this is the total time over all the permutations in which the first key is I still. So, it is this quantity. In total time to insert all the n keys in permutations where the first key is I. So, what is the total time to insert all the n keys in all the n factorial different permutations? It is just the sum of this quantity as I goes from 1 through n, because the first key can be 1 or 2 or 3 or whatever. Yeah. So, it will be just n minus 1 factorial times this sum, where sum goes from I 1 through n of this quantity. Are there any questions till this point? If you have questions, please ask, because it is going to get more difficult. Right. All I am doing is trying to figure out what is the total time taken to insert all the n elements, right, not in one permutation, but over all n factorial permutations put together. Yeah, and I am trying to do it in a way so that it is amenable to analysis.
In the earliest part, you told that when we fix the I element as the first element, as the root, then the I minus 1 which are less than that,
yes,
will be present in I minus 1 factorial. You meant that they will be present as that in the input sequence or in the root or in the tree as I minus 1 factorial permutation. Input sequence.
There are I minus 1 factorial different permutations of I minus 1 elements. That is all I am saying, right. Now, in the sequence of 1 through n, those I minus 1 elements are present at different places, right. All possible permutations of those I minus 1 elements are there. So, I minus 1 factorial different permutations of those I minus 1 elements are there, but each of those permutations itself is occurring n minus 1 factorial over I minus 1 factorial times, right. So, we have to keep that in mind. Okay. So, this is what we will carry on forward. So, forget about everything, but what we will work with now is this expression, which says that the total time to insert all the n keys is this thing. This is exactly the 16 we had computed for T3. Yeah, this is exactly that 16. So, now what is the average time to insert n keys? It is basically, this is the total time. So, this divided by n factorial would be the average. So, I have just divided that by n factorial, and this is what I would get. So, just to make sure, this divided by n factorial will give me 1 by n, and this expression, yeah. So, is just this that I have written, I going from 1 through n, right. Now, note that these terms will appear, each of these terms will appear twice, right. So, if I look at T3, it will appear once as for I equals 3, I equals 4, and it will appear once as I equals n minus 4, n minus 3, sorry. Yeah, so each of the terms will appear twice, so that this part of the sum, just this part, is 2 times ti, I going from 0 through n minus 1 now, and this part I have moved out. So, it is n minus 1, this is n minus 1 n times, divide by n, so it just becomes n minus 1. So, this n minus 1 is not multiplied by the 2 by n, this 2 by n only multiplies this part. Why does I go from 0 through n minus 1 now? Well, because you will never generate t of n, right, neither from here nor from here, and you will generate t of 0 when I equals 1, you will have t of 0, when I equals n, you will again have t of 0. Yeah, so you will have a t of 0. And what is t of 0? T of 0 is 0. In fact, t of 1 is also 0. Yeah, t of 2 is not 0, but t of 1 is 0 because it's just single element, right? We say it's at level 0, so we just don't count it any time for inserting it, right? So such a thing is called a recurrence relation. This is a function t, which is a function of n. We are expressing the value of this function at point n in terms of its value at previous points, right? So I can use this relation to compute t of 0, t of 1, t of 2 and so on. So t of 0 is 0. So what is t of 1? T of 1 equals 2 over 1 times t of 0. T of 0 is 0. So this term goes away. So n equals 2, n equals 1. So 1 minus 1 is 0. So t of 1 is 0, which we just argued that t of 1 is 0. So t of 0 and t of 1 are both 0. So I can now use that to compute t of 2, right? So what will I get the value of t of 2 as? Right. So if I were to just use this expression, I would get something like, let's see, I would get t of 2 would be equal to 2 over 2 times t of 0 plus t of 1, both of which are 0, plus 2 minus 1. So this entire thing is a 0, so thus it becomes 1. So t of 2 also turns out to be 1, right? And if you are not convinced so far, let us also compute t of 3. So t of 3 will be 2 over 3 times t of 0, which is 0, so let me ignore that, t of 1, which is also 0, let me ignore that, t of 2, which is non-zero, so let me leave that around, plus n equals 3, 3 minus 1, t of 2 was 1, so this becomes 2 over 3 plus 2, which is 2.66, which is exactly what we computed. Yeah, but you can now use this recurrence to compute anything, any t of I. Everyone with me on this? So we have done something fairly sophisticated here, right? We have obtained some kind of a relation which tells us any t of n, provided we know the previous values. But we will do a little bit more. We will try and figure out how to solve this recurrence relation also. Okay? And that is what we are going to do now. So t of, what did we say here? T of n is 2 over n times the sum of the previous t's plus n minus 1, right? So I can write t of n minus 1 is 2 over n minus 1 times the sum of the previous t's plus n minus 2, right? I just replace the n by n minus 1, and so I can just rearrange this. So this quantity then, or 2 over n times this sum, equals what? So what I have done is I have moved this n minus 2 on this side. So I get t n minus 1 minus n plus 2, and I have scaled it by n minus 1 over n because I am trying to compute 2 over n instead of 2 over n minus 1. So if this were 2 over n minus 1 times this, it would just have been this part. Yeah. So if you cancel out the n, so 2 over n minus 1 is exactly this part, which is what. Why am I doing this? I want to compute this quantity, right? Because now I am going to substitute this in the previous expression. So note that what I have computed is 2 over n sum of t's I going from 0 through n minus 2, right? So I am going to substitute that part here, Okay. So, I have computed 0 through n minus 2 as this quantity. So, I am going to substitute that. So, T of n then becomes this sum here, right? और अब क्या बचता है मेरे पास?
T of n minus 1.
n minus 1 बचता है, T of n minus 1, 2 over n into T of n minus 1 plus n minus 1. So, 2 over n of T of n minus 1 plus n minus 1, right? And then I just did some rearrangement. So, I look at T of n minus 1. So, it is n minus 1 over n here and 2 over n here. So, that makes it n plus 1 over n, and this is n minus 1 over n into n. N minus 1 over n into n is okay. So, what's the best way of looking at this? This is just n minus 1.
So this will cancel out with,
Yeah, n minus 1 over n is minus of n minus 1, which cancel outs with this, good. And so, I am just left with 2. So, it is just 2 times n minus 1 over n. Yeah. So, we will work with this now. So, all I have done is some rearrangement to simplify things. Now, I have written T of n just in terms of T of n minus 1. Abhi tak T of n was in terms of all the previous T's, right. So, this is the simplification I have achieved at this point. Okay. Let us see what I am doing. So, it is a bit of a dense slide, but we will run through this very quickly. So, this is what we have, n plus 1 over n times T of n minus 1 plus 2 times n minus 1 over n, right. Now, I have just replaced this by this is the same as this, but 2 times n minus 1 over n is less than 2, because n minus 1 is less than n. So, this is, so this, that is why the less than or equal to, actually it should be strictly less, yes, because n minus 1 over n is strictly less than 1, right. So, I just simplified this a bit, and now I am going to do the following. I am going to replace T of n minus 1 by using this recurrence relation, this expression. So, ये n plus 1 by n तो ये है. So, T of n minus 1, if you use this, is 1 plus 1 over n minus 1, which is n over n minus 1, times T of n minus 2 plus 2, and where is this plus 2 coming from? From the this plus 2, right. All I have done is replace this with this. Yes, everyone with me? Right. All I did was replace this part with this expression, right. And now, let me just simplify it. So, well, this n and n cancel. So, I get n plus 1 over n minus 1 times T of n minus 2. This 2 is this 2, and 2 times n plus 1 over n. That is what I get. Right. So, this is just a simplification of this, it is exactly equal. Now, once again I am going to play the same game. I am replacing T of n minus 2 with the value of that. So, what is T of n minus 2? T of n minus 2, what is T of n minus 2? It would be n minus 1 over n minus 2 T of n minus 3 plus 2. Actually, it will be less than or equal to this quantity. Yeah. So, that is what I am going to replace it by. Now, when I, so n plus 1 over n minus 1 times n minus 1 over n minus 2. So, the n minus 1 cancel, and I get n plus 1 over n minus 2 times T of n minus 3. This multiplies with this 2 to give me 2 times n plus 1 over n minus 1. And what is this part? This part is the same as this here, is the same as this one here. Yeah. So, you can just do this at home and see that this is what you will, and now this extends in this manner, right. When I replace it by this, I get this n plus 1 over n minus 3. This quantity keeps decreasing with every step, and this sum inside keeps increasing with every step, increasing. So, next time I will add 1 over n minus 2, the next time I will add 1 over n minus 3, and so on and on, right. So, that eventually this will go down to, when this goes down to n minus n, so I get a 0. This would be, the denominator would be n minus n plus a 1, or n minus a 1. So, it will be 1. So, I get just this thing, and inside here I will get all the terms going up to 1 by 2, yeah, and plus a 2. And so, this is exactly, since T of 0 is 0, this part goes away, and so I get exactly this. So, I get T of n is less than or equal to this sum. What is this? This is your harmonic series, right? The sum of a harmonic series. Half, 1/3, 1/4, 1/5, so on and on, going up all the way up to 1 by n. Right? What is the sum of a harmonic series? Anyone? Huh? It cannot be calculated. So good, you will learn something new in this course. Okay, so we are summing a harmonic series. So we have to sum 1 by 2 plus 1 by 3 plus 1 by 4 up to 1 by n. Okay. Now one trick that we employ very often, we take this graph. This is a graph of the function 1 by x, right? Okay, these are points 1, 2, 3, 4. So let me draw a line here at 2. So what is the height of this? What is the height of this rectangle? 1 by 2. Yeah. What is the width of this rectangle? 1. So इसका area कितना हो गया? 1 by 2, half. इसका 1 by 3 हो जाएगा ऐसे, क्योंकि I have drawn a line here at 3. 1 by 3. Yeah. So area 1 by 3. So I'm getting the terms here. So next one 1 by 4, 1 by 5, 1 by 6. The last one at n, I'll draw it in this manner. So this sum is the area under the curve fx equals 1 by x, is at most the area under the curve in between the limits 1 through n. Yes? Right? So this sum is less than or equal to the area under the curve under the curve 1 by x between limits 1 through n. So now recall what was our T of n. T of n was, okay, T of n was 2 times n plus 1 into this harmonic sum plus a 2. So I am going to just put that 2 times n plus 1. That harmonic sum was the integral of 1 by x, was at most the integral of 1 by x from the limits 1 through n plus a 2. This is log of x, right? X equals n पे log of n हो गया, x equals 1 पे 0 हो गया, so it will just be log of n. So this is exactly this sum, which is order n log n. So T of n is less than or equal to order n log n. Right? So the expected time for inserting the n keys. So what have we done? We have actually done a very sophisticated computation here. Yeah, and you have also understood it, right? Isn't that surprising? So what are we saying? We are saying we looked at all the n factorial different permutations possible. We computed what the total time taken to insert all those n factorial different permutations was, and we took the average. And what did we get? We got n log n. Yeah. Recall we saw the worst case was n squared. Right? There is a particular permutation which is just put the elements in increasing order. For that, the total time for insertion is n square. But the average time is n log n. Right? And what is the best time? The best time is also n log n. Why? So the best time would happen when the tree was very shallow. Right? And the tree, so if you have a tree of on n nodes, it has a height at least log n. We've seen that. Log n minus 1 or some such thing, or roughly this. Right? So if it has height log n, that the last level you have a lot of keys, right? In a tree of height log n, if you take a complete binary tree of height log n, the last level has n by 2 keys. The leaves, there are n by 2 leaves. To insert each one of those leaves, you will take how much time? Log n, because you'll have to come down the entire tree. So to insert each one of those n by 2 keys, you are taking log n time. So you are just to insert the leaves, you take n by 2 log n time, n by 2 times log n time, right? Which is omega n log n, right? A function which is growing faster than n log n. Some constant times n log n, but n log n, right? So in the best case, you are taking n log n time. In the worst case, you are taking n square time. So the best case is n log n time. The worst case is n square time, but the average case is also n log n. That's a very interesting part. Right? If I would ask you the average case, you would perhaps be tempted to just take the average of these two numbers and report that. Yeah. But why is it turning out to be this? What does it convey? What does it convey? Most of the trees are fairly shallow, don't have too much depth. Most of them have trees, most of the trees have depth of only about log n or some constant times log n. So that the average is still only n log n. Yeah? You follow this? So the best, you have a bunch of numbers. The numbers here are the total time for insertion under the various permutation. The smallest of those numbers is n log n. The largest of those numbers is n square, but the average is also n log n or some constant times n log n, right? Which means that most of the numbers are closer to the minimum than to the maximum. Okay, so that's all I was going to discuss in the class today. What we discussed today was the deletion procedure, and then we also discussed this particular analysis, which says that if you were to take a random permutation of n elements and insert them, then the average time, then the expected time for insertion is n log n. The worst case, there could be a permutation for which the time taken is n squared. Right? That is the worst case, and we have seen examples of those. If the elements are in increasing order or in decreasing order, then you take n squared time. The best case, the best possible permutations is also going to take at least n log n time, some constant times n log n time, right? But the average case is also n log n. Okay, so we stop with that.
Hello everyone, I am Nitika Arora, Assistant Professor of Computer Science from Shaheed Udham Singh Government College, Matak Majri, Indri. Today the topic is deletion from binary search tree, in which we discuss about how to delete any node from binary search tree in different conditions. So there are some questions based on this topic. Question number 1. What is binary search tree insertion and deletion in binary search tree? Question number 2. How do I delete a binary search tree? Question number 3. What are the disadvantages of binary search tree? Question number 4. Which one is better, linear or binary search? Question number 5. Is deletion in binary search tree commutative? Is deletion in binary search tree commutative? Question number 6. What are the limitations of binary search tree? What are the limitations of binary search? So these are the questions based on your topic, deletion from binary search tree. Discuss all these questions with your class teacher and then write down the answers on your notebook. Thank you.